Welcome to the class, children. In the last class, we discussed the definition of a set, types of sets, set operations, and Venn diagrams. Now, let us continue our class by defining some more terms. Of these, difference of two sets. The difference of two sets A and B is defined as the set of all the elements in the set A which are not in the set B. It is denoted by A minus B. Now let us take one example. A is equal to set of 1, 2, 3, 4, 5 and B is equal to set of 4, 5, 6, 7. Now let us find the difference between the sets A and B, that is A minus B. By the definition of the difference of two sets, we can say that we have to consider the elements which belong to A. Those elements should not belong to B. So what are the elements which belong to A and not belong to B? Very clear. They are the elements 1, 2 and 3. Because the elements 4 and 5 belong to second set B. That's why we should not consider the elements 4 and 5. So for A minus B, we have to consider the elements 1, 2 and 3 only. Finally, we can say that A minus B is equal to set of 1, 2, 3. In the same way, we can find B minus A also. So, to find the elements in the set B minus A, we have to consider the elements which belong to only the first set B. And those elements should not belong to second set A. So, what are the elements which belong to only first set B in the second case? That is 6 and 7 only. Those elements do not belong to second set A in this case. So B minus A can be defined as set of 6, 7. So from this example, we can describe the set A minus B in the set builder form as set of X such that X belongs to A and X does not belong to B. Now let us describe the set A minus B through the Venn diagram. So for that, let us take a rectangle to represent a universal set and two circles to represent the sets A and B. To represent the set A minus B, first of all, we have to find the region which belong to A but not to B. So how to identify? For that, first let us neglect the region of the set B and now consider the remaining part of A. What is the remaining part of A? Here, this is the remaining part of A. Now, here let us shade this remaining part of A with horizontal lines, red color horizontal lines. Now, this is the region which belong to only A but not to B. So, this region will represent the set A minus B, and in the same way we can represent the set B minus A also. For this, first we have to neglect the region of A, the entire region of A, and now you consider the remaining part of B. Okay, now let us the remaining part of B with vertical lines colored with green. Now this region will represent the set B minus A. This is about the Venn diagram of A minus B and B minus A. And also students, here we can observe one thing. Between the sets A minus B and B minus A, here we can see the unshaded region. This unshaded region will represent the set A intersection B. Of course, already we have discussed this operation A intersection B. And also we can observe that the sets A minus B, A intersection B and B minus A together will constitute the set A union B. So A union B can be taken as A minus B union A intersection B union B minus A. The next definition is symmetric difference of two sets. The symmetric difference of two sets A and B is defined as the set of all the elements which are in A or in B but not in both. The symmetric difference of the sets A and B is denoted by A delta B like this. Now let us try to understand this operation with some example. A is equal to set of 1, 2, 3, 4, 5 and B is equal to set of 4, 5, 6, 7. Now by the definition, A delta B can be taken as set of 1, 2, 3, 6, 7. Here, if you observe, the elements 1, 2, 3, they belong to A, first set A, but not to second set B. It is nothing but A minus B. So, the set of the elements 1, 2 and 3 belong to the set A minus B. And you take the remaining elements 6 and 7. These two elements belong to the set B but not to A. So 6 and 7, the elements 6 and 7 belong to the set B minus A. So from this we can understand that A delta B is equal to A minus B union B minus A. And also we can define the set A delta B in another manner. Here, if you observe, here we have taken all the elements from the first set A and from the second set B, leaving the common elements. So, A delta B can also be defined as A union B minus A intersection B. Now let us define the complement of a set. The complement of a set A is defined as the set of all the elements of the universal set mu which are not in the set A. It is denoted by A complement, either like this or with this notation. Let us take one example. Mu is equal to set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And B is equal to set of 2, 4, 6, 8, 10. Now let us define the complement of the set A. So by the definition, the complement of the set A is the set of all the elements in mu but not in A. That is nothing but A complement is equal to mu minus A. So already we have discussed the difference of two sets. So by the definition of difference of two sets, now mu minus A can be taken as set of 1, 3, 5, 7, 9. Now we can describe the set A complement in the set Euler form as set of X such that X belongs to mu and X does not belong to A. Now let us see the definition of a power set. The set of all the possible subsets of the given set A is defined as the power set of A. The power set of A is denoted by P of A. Let us see one example. A is equal to set of 2, 4, 6. Now let us write the subsets of A. First let us write the subsets with the single elements. Set of 2. Set of 4, set of 6. Now let us write with the two elements, set of 2, 4, set of 2, 6 and set of 4, 6. Let us write with the three elements. Three elements means the same set you will get. So we know that every set is a subset of itself. That's why A can be taken as subset of A. So A is one of the subsets. And also we know that null set is a subset of every set. That's why for this set A, we can take null set also as subset. Now, these are all the possible subsets of the given set A. If you take the set of all these subsets, now this set is defined as power set of A. Now let us see the first one, that is commutative law. That is A union B is equal to to B union A. Now we can easily say that A union B and B union A are equal by the element wise proof method. For that, let us take one element in A union B, that is X belongs to A union B. It by implies that X belongs to A or X belongs to B by the definition of union of two sets. And also we can say that X belongs to A or X belongs to B as X belongs to B or X belongs to A. Because if you say book or pen or book, both will give the same meaning. They will not give any different meaning. That's why X belongs to A or X belongs to B can also be written as X belongs to B or X belongs to A. It also implies that X belongs to B union A. So from this we can conclude that A union B is equal to B union A. And in the same way, we can also say that A intersection B is equal to B intersection A. So we can state that union of two sets is commutative and also intersection of two sets is commutative. Second one is associative law. For this, let us take three sets A, B and C in the same order two times. A, B, C, A, B, C. Now for the first set, let us find union between A and B. Later, let us find union between the A union B and C. Come to second set. First let us find union between B and C. Later let us find union between A and B union C. In both the ways you will get the same result, that is A union B union C is equal to A union B union C. This is known as associative law. So the union of the sets is associative. Similarly, the intersection of the sets is also associative. That is, A intersection B intersection C is equal to A intersection of B intersection C. Next one is distributive law. That is, A union of B intersection C is equal to A union B intersection A union C. Here we say that union distributes over intersection. And in the same way, we can also say that intersection distributes over union. That is, A intersection of B union C is equal to A intersection B union A intersection C. Idempotent law. That is, if A is any set, then A union of A is equal to A and A intersection of A is equal to A. This is known as idempotent law. Identity laws. In this two identities are there. Let us see the first one. A union phi is equal to A. Now let us see how it is true. For that, let us take one element in A union phi, that is X belongs to A union phi. It by implies that X belongs to A or X belongs to phi. So here it is very clear that X belongs to phi is false case. So we can say that X belongs to A. So by implies X belongs to A. Now from this we can say that A union phi is equal to A. Like that, the union of any set with the null set is the set itself. So the null set is identity element for the union of the sets. In the same way, the universal set is the identity element for the intersection of the sets. That is, A intersection mu is equal to A. The next one is complement laws. In this, first law is A complement whole complement is equal to A. Now let us understand this law through the Venn diagram very easily. For this, let us take a rectangle and a circle to represent a universal set mu and a set A. Now, let us draw the Venn diagram for A complement. We already learned that A complement is equal to mu minus A. We already know that A complement is equal to mu minus A, which means we have to identify the region which belongs to mu but not to A. So this is the region which belongs to mu but not to A, that is A complement. Now for this A complement, again you have to find complement, that is A complement whole complement, which is mu minus A complement. Now what is the region which belong to mu and not belong to A complement? It is very clear. This is the region which belong to mu but not to A complement. It is nothing but set A. So from this we can say that A complement whole complement is equal to A. Next one in this law is A union A complement is equal to mu. Now in the same Venn diagram, let us take the sets A and A complement. Here the region with horizontal lines will represent the set A and the region with vertical lines will represent the set A complement. Now tell me, if you consider the union of these two sets, it is very clear that you will get the universal set mu. So A union A complement is equal to mu. And in the same way, you take intersection of A and A complement. So can you find the intersection of A and A complement? It means, can you find any common region between the set A and A complement? No, there is no any common region. That's why A intersection A complement is equal to phi. And in the same way, mu dash is equal to phi and phi dash is equal to mu. So finally complement laws are A complement whole complement is equal to A union A complement is equal to mu, A intersection A complement is equal to phi dash is equal to mu and mu dash is equal to phi. And the following four laws are De Morgan's law. Children, let us see how this set theory is useful in the practical problems. For this, let us try to understand the meaning of the sets in different combinations. For that, let us take mu is equal to set of x such that x is a natural number. A is equal to set of x such that x is a multiple of 2. The set B is equal to set of x such that x is a multiple of 3. And the set C is equal to set of x such that x is a multiple of 5. Now let us try to understand the meaning of these sets in different combinations. First, let us take A union B. This set A union B gives the meaning in this situation that set of x such that x is a multiple of either 2 or 3. If you take the set A intersection B, it gives the meaning that set of x such that x is a multiple of both 2 and 3. In the same way, let us see the meaning of these sets in a different combination. If we take the set A minus B, it gives the meaning that set of x such that x is a multiple of 2 which is not a multiple of 3. If you take the set A complement, it means set of x such that x is a natural number which is not a multiple of 2. The next one is A union B whole complement. It means set of x such that x is a natural number which is a multiple of neither 2 nor 3. It means this set A union B whole complement does not contain the multiples of 2 and also multiples of 3. So in this case we can write A union B whole complement as set of 1, 5, 7, 11, 13, 17, 19, 23, 25 and so on. Here we can observe, here we can't see the multiples of 2 and also the multiples of 3. The remaining natural numbers we have taken for the set A union B whole complement. Next set A intersection C whole complement. It means set of x such that x is a natural number which is not multiple of both 2 and 5. Which means if any number is a multiple of both 2 and 5, that number is not taken into the set A intersection C whole complement. For example, let us take the number 10. It is a multiple of both 2 and 5. That's why this number 10 does not belong to A intersection C whole complement. If you take the number 6, it is a multiple of 2 but not 5. So 6 belongs to A intersection C whole complement. And also let us take one more number 7. 7 is not a multiple of either 2 or 5. So the number 7 also belongs to A intersection C whole complement. So for the set A intersection C whole complement, we should not consider the common multiples of 2 and 5, that is 10, 20, 30, 40, 50 and so on. Leaving these elements 10, 20, 30, 40, 50 and so on, we have to consider all the remaining natural numbers for the set A intersection C whole complement. If you take the set A intersection B intersection C complement, it gives the meaning that set of x such that x is a natural number which is a multiple of 2 and 3 but not a multiple of 5. So children, to use the set theory in the practical problems, we need to establish the relation between the sets and their combinations with the different operations. Let us see the first case. If A and B are disjoint sets, then we can show their Venn diagram like this. In this case, to find the total number of elements in A union B, it is enough to add the number of elements in A and the number of elements in B, because no element is in common. That's why the sum of number of elements in A and the number of elements in B will give the number of elements in A union B. If A and B are joint sets, then their Venn diagram can be shown like this. In this case, the sets A and B have some common elements. So here, the sum of the number of elements in A and the number of elements in B can't be equal to the number of elements in A union B, because they have some common elements. So in this case, already we have seen one relation. A union B can be taken as A minus B union A intersection B union B minus A. Already I have explained this relation. Now in this case, to find the total number of elements in A union B, we have to add the number of elements in A minus B, the number of elements in A intersection B, and the number of elements in B minus A. So from this we can write it as n of A union B is equal to n of a minus b plus n of a intersection b plus n of b minus a. Now let us see the derivation of the relation between a, b, a union b and a. Now let us try to derive the relation between the cardinal number of the sets. For this, let us observe from the Venn diagram that n of a is equal to n of a minus b plus n of a intersection b, which means n of a minus b can be written as n of a minus n of a intersection b. So from the previous relation, that is n of a union b is equal to n of a minus b plus n of a intersection b plus n of b minus a. If you replace n of a minus b and n of b minus a by the above relation, we can get that n of a minus n of a intersection b plus n of a intersection b plus n of b minus a can be written as n of b minus n of a intersection b. If you cancel plus n of a intersection b and minus n of a intersection b, you will get the relation n of a plus n of b minus n of a intersection b. This is the relation between the cardinal number of the sets a, b, a union b and a intersection b.